Hi, and welcome to the November edition of According to Pete. Today, we're going to cover transistor biasing configurations, which is probably kind of a wacky thing. I had originally thought that, hey, I'm going to do MOSFET biasing circuits. That'll be cool. And then I figured out, well, I don't know anything about MOSFET biasing circuits yet. Instead, I'm going to back up a little bit and do transistor biasing. I thought, great, I can cover common base and common collector and common emitter in one video. No, you can't do this in one video. That's insanity. So today, I'm going to cover common base configuration, which honestly is very rarely used, and common emitter configuration, which is more often used, but not as much as the third one that we're going to do later, called common emitter. So for the case of, or for the sake of argument, for the sake of our examples, we're going to talk about standard small signal NPN transistor. Remember this guy? Points to the N material, so NPN, sort of like that. Imagine this to be your standard garden variety 2N3904. We all know them, we all love them. If you will recall, a little bit of review, you get a small current going from base, that is not a B, to emitter, and that gives you a large current that goes from emitter or collector to emitter, okay? So the proportion, there's a proportion for how big this current is to how big this current is, and that is called, if you look at the data sheet, HFE, or beta, okay? And that number for 2N3904 is something on the order of 100 to 300, depending on where you have the transistor biased. The idea is like, so 1 microamp through the base emitter junction will give you, 10 milliamps at a factor of 100 going from collector to emitter. The first thing you gotta do before anything else can happen, you got to turn the transistor on. You get a small current going through here, gives you a large current going through here, right? Which means setting it up with a DC quiescent state, right? Because the reason we want to use this thing is to pass an AC signal. Could be audio, could be RF, could be a sensor, could be a lot of different things. In general, what you do is you set up this voltage divider, R1 and R2, so that you have a known voltage here, which, you know, for the sake of argument, we'll just say is V plus over 2, which it's not necessarily ever going to be, but just because we're starting someplace, right? Now, for this being a 2N3904, you can expect, right, this is a diode, right? We talked about that in the previous, if you don't remember some of this stuff, go back to the transistors episode that was way long ago and review some of this, okay? This is a diode. And you got to turn this guy on, and you can assume that this is about 0.6 volts drop from here to here. So if you know you've got V plus over 2, half of VCC, then you know that you've got 0.6 volts less than that here. If V plus was 10 volts, which you totally cannot read, 10 volts, then that makes this 5 volts, and that makes this 4.4 volts, okay? 4.4 volts. You set up your emitter collector current with that resistor, all right? You know you got 4.4 volts here, and in the process of designing the circuit, and we'll get to some of that, be cool, you calculate this value to give you your current through emitter to collector using Ohm's law, okay? So if I wanted 5 milliamps going through here, I would say, okay, 4.4 volts divided by 5 milliamps is X ohms, and I would set that value to be X ohms. And then these are just a resistor divider, but their values can become critical depending on the application. And this will become clearer as I go. This guy is typically used for setting up an operating point or limiting currents through this thing. And that'll become clearer again. I keep saying that, right? General concepts right now. The first thing you want to do is turn it on with regard to DC. And this is what we're doing. We set up our divider, we figure out our voltage here, we figure out how much current is here, and these are all going to be iterative. When you're working with stuff like this is not an exact science, all right? This is an iterative process. If you've been watching my shows for all this time and you think that electronics is a precise thing, you've been not paying attention, brother or sister. This is iterative, and always plan for it to be. It's never going to come out just perfect. Now, the first configuration I'm going to talk about is called common base. And I start with this one because this is the low-key one. It's probably not low-key at all, but it's the one that is least commonly used, so call it uncommon base. You put an input on the emitter, which is unusual, and you take your output from the collector, which is not unusual. The input impedance, right, so the amount of current that this circuit is going to try to draw off of the source, it'll try to draw all of the current. The input impedance is very low, okay? Like on the order of less than 10 ohms typically. And the output impedance is rather high. In fact, it is said that the source impedance, or the source current is carried all the way to the output. And in fact, your Z out is approximated by R source, whatever this is internal resistance is, divided by the beta of the transistor. So it's not a great thing. Its current gain is a little bit less than 1. Its voltage gain can be quite high. Problem is, the voltage gain is difficult to calculate and is highly dependent on the thermal voltage of the device. Oh my gosh, go look up Boltzmann's constant. Yeah. The gain is unpredictable, the current gain is terrible, and the input impedance sucks. So for that reason, this configuration is generally relegated to things like the front end of a radio, where you're trying to match the impedance of an antenna. This is terrible at low frequencies, and the reason is because the input impedance is only a few ohms. And remember this this equation, 1 over 2 pi RC. That is F. That's your corner frequency for this input impedance and that capacitor. So you're going to try to calculate that capacitor based on that. And the lower the frequency is, and the lower that resistance is, the more awful that cap is going to become. So at low frequencies, this thing is just about completely unworkable. What I know is that this circuit is used for voltage gain, okay? So I'm going to have a large swing on the output, which is at the collector. Now, the first thing I do is I go, my supply voltage is 10 volts. So I want my quiescent operating point of my output to be at half of that, okay? So I know this is going to be 5 volts. 5, not even close to writing. Hooray, 5 volts. Okay, that's a choice. That is something I want my output to be able to swing up to 10 and down to 0 as cleanly as possible. So I set that there. I know that this voltage has to be less than that. I don't know how much, but since I've never set one of these up, I took a guess, right? I just want to see where it ends up. So I set this value to 2 volts. I also know that the input impedance or the input, the Rin, if you will, is going to be the thermal voltage divided by the, I'll just write it down. So Rin, I hope you can read this a little bit, equals VT over IE. IE is the emitter current, okay? VT is the thermal voltage, and if you look this up, it is highly dependent on the temperature of the junction, okay? At room temperature, the thermal voltage is about 20, wow, does this suck? 26 millivolts, okay? It's a small number. If I just choose a value, and for the sake of my example, I just chose a value because I wanted to see what would come out, and I chose it to be 5 milliamp. With that value at room temperature, Rin comes out to be 5.2 ohms. That's nuts. More importantly, with my choice of that, my choice of 2 volts, I know that 2 volts divided by 5 milliamps is going to be 400 ohms for the value of RE, our emitter. Now I also know that since I've chosen my my quiescent point to be at 5 volts, so I get maximum upswing and maximum downswing at 5 milliamps, I have a value of 1K for my RC, which is the resistor collector. Resistor collector. I collect resistors. So I've got values for this, I got values for this. I know that's 2 volts, and I assume that this point is going to be 2.6 volts, okay? Because we know that the voltage drop across this from base to emitter is about 0.6 volts. Now, that's not a guarantee, that's an assumption. It could be anywhere from 0.55 up to 0.75, and it's going to depend on device to device. From there, I just got to set up my divider for 2.6 volts. How much current has to go through this divider? That is a little bit of a critical question. When you set these guys up, and this goes for any of these configurations that we're going to talk about, you generally want your divider current, which goes to be a factor of 10 more than the current that you know is going through here, okay? So if I've chosen 5 milliamps to go through here, and I know the beta of this transistor, which is also variable, but if I assume it to be 100 for a small signal device like this, that's not a bad assumption. I can assume it, you know, if I've got 5 milliamps here, I've got 50 microamps that's going this way, okay? So I want a factor of 10, so like 500 microamps going here. Now for the sake of my example, I didn't do that. I swamped the heck out of it. And I just said, yeah, make that 5 milliamps too. Sure, what the heck, 5 milliamps. And so now it's just a matter of calculating resistor values, okay? So for R2 down here, I got 520 ohms. And for R1 up here, I got 1480. Now you're going to calculate all kinds of values that are not particularly standard, okay? So you're going to have to make the choice. Am I going to create a resistor? Am I going to make do with what I can get my hands on? Let's talk about how we expect it to work, right? So if you got an input here, and I always encourage like a mechanical understanding of what you're actually looking at. So you're putting in a signal at V in, right? So there's an instantaneous voltage that occurs at this point, because for that cap signal, that's a short, right? So you can expect, you know, your signal is going to appear there, and that's not even going to be in the circuit. So with that, if your V in is going low, what's going to happen here? It's going to pull this point low, and since the base is stable, it's going to turn that sucker on really hard, right? So when this guy turns on much harder, it becomes a smaller resistance, right? So it's going to bring this value down. So the output's going to go down. Now when you send the input high, just the opposite. It's going to bring this point higher, and it's going to shut off the transistor because your base is held at 2.6 volts, right? So this becomes a larger resistor, and so you're going to have a positive going signal. So what this tells us is that your input and output are in phase. My input impedance for my choice of emitter current is 5.2 ohms. That is not very good. It may occur to the viewer that, in fact, the input impedance is not just this, but it's this and this, right? Well, okay, first thing, point out, these resistors aren't even going to enter into the equation. And the reason is because of that cap right there, because that's an AC ground, okay? So these resistors, it's not really very critical what their values are necessarily, unless this is like, you know, depending on how much branch current you want through here, you increase their values, but they're not going to come into the input impedance equation because that is signal ground, okay? This guy will also not come into it because he is 2 orders of magnitude above what we're looking at. So that's not going to come into the equation either. So it's basically going to be that. Now I can improve that, right? If I chose this resistor value, right, still 2 volts, but if I chose this to not pass 5 milliamps, but to pass 1 milliamp, for example, I could increase that by a factor of 5. Still not great, but it's better. The voltage gain of this circuit is not very easily predicted, and it's highly dependent on the value of emitter current. The greater your emitter current, the greater your voltage gain, the lower your input impedance. This is called the emitter follower, or common collector. The idea here is that you put a signal in on the base, and you take the output at the emitter. So the emitter follows the base. Characteristics of this circuit are a high, relatively speaking, a high Z-in, input impedance, and a relatively low output impedance. So it's a current driver, okay? Now, because this voltage follows this voltage, your voltage gain is going to be just slightly less than 1. Now you notice there is no resistor or collector resistor here, and that's to facilitate lots and lots of current going to your load ultimately. If you put a high going signal on the input, you know this point has to be within 0.6 volts of that, right? So if you put something in here, this is going to be 0.6 under it. So you're going to have a high going there. So your input and output are in phase, just like the common base. I assigned myself a value of VCC to be 9 volts because I don't want to make anything easy by making it 10 volts again. If I know my output signal is here, and I know that I want it to be halfway between VCC and ground, then I know that this is 4.5 volts, okay? I know that point's going to be 4.5 volts. And because I know that, I know this point is going to be 5.1 volts. We want to choose a quiescent current, which is, you know, the current that it's going to have running through it with no input signal. And we want to choose it to be sort of low. And the reason we want it to be sort of low is because we want this transistor to be able to source all of its extra current through the load. We don't want it going this way, we want it going that way. I chose this value, again, to be 5 milliamps. So if I got 5 milliamps going this way, and I know I got 4.5 volts here, then I immediately know that my value for RE, which is down there, is going to be 900 ohms. Now, choosing values for these guys. Same rule as with the common base, which is to say that whatever your base emitter current is, you want your branch current here to be like a factor of 10 above that to swamp out the effects of that thing. So if I've got 5 milliamps here, and I assume a beta of about 100, then I've got 50 microamps going yay-wise, 50 microamps. And a factor of 10 over that is 500 microamps. But me being me, I just chose a value, and I said it was 2 milliamps. To set up 5.1 volts at 2 milliamps, the numbers I got were 2250, oh, that's gonna be really icky, 2250 ohms for R2, and for R1, I got 1950 ohms. As I was saying before, the input impedance on this circuit in general is considered relatively high. To calculate it out completely, what you're looking at, right, a signal going here is going to be actually this resistor, R1, in parallel with R2, in parallel with beta times RE. For the sake of this, this example, I assumed a beta of 80. I don't know why I did that, okay? I just did it. So what we're talking about is 1950 in parallel with 2250 in parallel with, I calculated it out, 72K becomes that resistor. So when you add up all of those in parallel, you get a whopping 1392 ohms. 2 milliamps might not have been a very good choice. A factor of 10 on that would bring me down, like I said, to 500 microamps, which is much better. In fact, I recalculated all of that stuff, and I ultimately got, you know, if you assume this is 500 microamps, these numbers change to 7,800 for that guy, and 10,200 for R2, and so your parallel input impedance becomes 4164. So it's about a factor of 3 better. I can also drop my emitter current. This does not have to be 5 milliamps. I could drop it to like 1 milliamp and I could get this number up even more. The source, whatever's coming out here, I don't want to tax it too very much. So the higher input impedance I get, the better that's going to be. The other thing is that cap, right? Once again, 1 over 2 pi RC equals F. The higher this number is, the lower that cap value can be, and it's easier to achieve a low value than a high value in a lot of cases. My output impedance is approximated, boy, this is getting really nasty, isn't it? Is approximated, Z out is about R source over beta, okay? So whatever the output impedance of this guy is, divide that by beta, and that's what you can assume out of here. Why would you use this circuit over an op amp or something else? Well, you wouldn't necessarily. The 2 circuits that I've shown you so far are not very interesting to me. The most interesting one is going to come when we talk about common emitter. And the reason you would use that one over an op amp, that one gives you voltage gain and current gain. And the reason you would use that one over an op amp is because op amps are optimized for linearity, whereas a transistor, you try to work really hard to make it linear, which sounds like a downside, but it isn't always a downside because it allows you to really jack with your signal in really interesting ways, okay? You can add harmonics, you can do mixing, it becomes kind of wacky. And the 3 configurations that I'm showing you are really only the tip of the iceberg. They're just enough to get you a little bit into it and then cut you loose and fly from the nest and see what you do. That's it for this time. Admittedly, the first 2, common base and common collector, are mildly interesting, but it's more to illustrate the process of setting up a bias on a circuit so you can use it like that with a transistor. Keep the questions and comments coming. Check out the engineering group at SFE_engineering on Twitter, or check out the SparkFun proper at SparkFun. Wait, you're looking the other way. At SparkFun. Send your questions and comments to feedback@sparkfun.com with according to Pete in the subject line, or put them in the comments section below. Thanks for tuning in, and I will see you next month.
Rant away.
And I'm zoning out.